This video is for section 7-5, applications involving radicals. Let's work a few examples together. Find the time t in seconds for a complete swing of a pendulum whose length L is 12 feet. So if you've had physics class and studied pendulums, you certainly have an advantage on this. But a pendulum is a weight that's on the end of a rope or string, and it swings back and forth. You start a pendulum swinging by lifting up the pendulum. Then when you let go, it will swing over this direction and then back to where it started. How much time does it take for one complete swing? To answer this question, we need to know the formula relating time and the length of a pendulum. That formula is T equals 2 times pi times the square root of L divided by 32. Then the question becomes just a matter of substituting the length. 12 divided by 32 is a reducible fraction, so this can be rewritten as 2 pi times the square root of 3 over 4. Then we can rewrite the square root of the fraction as the square root of the 3 over the square root of the 4. The square root of 4 is 2, and that 2 will cancel away the 2 at the beginning. So what's left over is pi times the square root of 3. We're told that time is measured in seconds. This expression gives an exact answer for the time, but on a problem like this, it might be more useful to have a decimal approximation. You could take a calculator and multiply 3.14 times the square root of 3 to get that decimal. Next example, find the circumference of a circle whose area is 128 square centimeters. The circumference of a circle is the distance around the outside of the circle. In this case, that would be measured in centimeters. The area of the circle is the amount of space inside the circle, which is measured in square centimeters. To answer this question, we need to know formulas. One formula is the circumference of a circle is 2 times pi times the radius. The other formula that applies is the area of a circle is pi times the radius squared. Hopefully you remember these formulas from algebra or from middle school math class. We're given the area, so we can substitute 128 in place of the letter A. Then we can solve this equation to figure out the radius r. The first step would be to divide both sides by pi. So we get 128 over pi is equal to r squared. To solve for r, we're going to take the square root. We only need to choose the positive square root this time because the radius will be a positive number, not a negative number. So the radius of this circle is equal to the square root of 128 over pi. We could simplify this answer up, but before we do that, let's think about what we're going to do with the value of radius. We're going to substitute it into the formula for circumference. So it's not necessary to simplify yet. Using our other formula, circumference equals 2 times pi times r. But we just figured out r was the square root of 128 over pi. Now we need to simplify. We can rewrite the square root of the fraction as the square root of 128 over the square root of pi. Next, we can rationalize the denominator by multiplying top and bottom by the square root of pi. Now our answer is 2 pi times the square root of 128 times the square root of pi all over pi. Notice that this pi symbol in the numerator will cancel away this pi symbol in the denominator. The number 128 is not a perfect square, but it can be factored using perfect squares. So let's rewrite this as the square root of 64 times the square root of 2. The square root of 64 is 8, which will get multiplied by the 2 at the beginning. 8 times 2 is 16. This square root of 2 is in a radical, and this square root of pi is in a radical. They can be combined under a single radical. We're finding the circumference of a circle, which is a distance, So our unit is centimeters. One more example. According to Kepler's third law of planetary motion, the cubes of the average distances of the planets from the sun are proportional to the squares of their times of one revolution around the sun. If Saturn is half as far from the sun as Neptune, find the ratio of their times of revolution. This problem involves direct variation. One way to answer this question is to model the direct variation. The distance cubed is equal to m times the time squared. Saturn's distance to the sun is half as much as Neptune's. So let's fill in the number 1/2 for D. This equation involves the planet Saturn. So to identify that this capital T is Saturn's time of revolution, let's give it a subscript, the letter S, to mean Saturn. If we use the number 1/2 to be Saturn's distance, then Neptune's is twice that, or the number 1. So 1 to the third power is equal to m times the time of Neptune squared. Let's solve both of these equation models for the time by dividing by m. So the time for Saturn to revolve around the sun squared is equal to 1/2 to the third power, which is 1/8, divided by m, which is 1/8m. For this equation, when we get the t sub n squared alone, we get 1 to the third power, which is 1, divided by m. Next, we can get the time of Saturn to revolve around the sun alone by removing the exponent of 2 using square root. So this becomes the square root of 1/8m. For the second equation, we can get the time for Neptune to revolve around the sun alone by doing a square root. We get the square root of 1/m. Then we can create a ratio of the times by dividing this time by this time. Time for Saturn compared to the time for Neptune is equal to this square root divided by this square root. Let's simplify this by applying the theorem that allows us to rewrite this as a single square root symbol. 1/8m divided by 1/m is equivalent to 1/8. Illustrate that over in the margin. 1/8m divided by 1/m, when you apply the rule about changing into multiply, becomes this. And the m's cancel away. Notice the answer is 1/8. This is not simplified because there's a fraction in the radical. So let's apply the theorem we just used in reverse and separate it into numerator and denominator. This becomes 1 over the square root of 8. The square root of 8 can be factored as the square root of 4 times the square root of 2. So this becomes 1 over 2 square root of 2. Now we can rationalize the denominator by multiplying top and bottom by the radical. We get the square root of 2 over 4. Make sure you understand where the 4 comes from. Focusing on the denominators, the square root of 2 times this square root of 2 makes a 2, which then gets multiplied to this 2 up front. We were finding the ratio of the time for Saturn to the time for Neptune. And after several steps of simplifying, our ratio is the square root of 2 over 4. In this lesson, we worked some word problems together that involved radicals. We had to combine our knowledge of science, specifically some math formulas from science, with our knowledge of algebra so that we could simplify our answers.